Alright, since some of you are here and I'm here already, I can share certain things before class that I think is kind of interesting. Alright, there we go. Screen share is on and YouTube is streaming as well. So anyone who wants to kind of catch up with stuff that I talk about before class can do so. So here's an interesting chart. I found this over the weekend when I was doing some research, and it shows you a lot of different types of information about computer science, like in terms of the workforce, in terms of age. The average age is 47.5%, and you can also look at the chart that shows you, the distribution of the people of different ages. So you can also see how there's a kind of a big drop off after 55-ish. Let's see, yeah. So 55, and the peak here is at 54. So that's kind of interesting because there's a little sharp increase here, and then it drops off, kind of in a monotonic way. The majority of people in CS or employed in the computer science field is 37 years old. So that's just kind of some random data that is kind of interesting. If you scroll down, okay, there's a gender, proportion, and then we have race and ethnicity. And then down here we have place of origin. And then down here we have skills. And I think this part is the most interesting part of it. So these are the skills, I guess either voted by participants or by employers, what skill is important in the field of computer science. So if you look at this bar over here, you would think it is programming, but it's not. It's actually reading comprehension. I was a little surprised. Okay, so reading comprehension is way up here, and then active listening is also way up here as well. And then then we have writing. Yeah, so isn't that interesting? I can share the Joplin notes afterwards, so you guys can have this data with you too. Yeah, no, we don't want to misread information. We also have to read programs written by other people, API descriptions, all kinds of technical documentation. So even though we are not reading literature, content, it is still very, very important. So when you actually get down to things that are very specific to programming, I mean, even judging and decision making, system analysis, and also systems evaluation, those are still ranked pretty high. And then this one here is complex problem solving. So that one is not really surprising. But what surprised me was reading comprehension and active listening. So that was kind of interesting. Yeah, understanding instructions and truth be told, my notes, can can be challenging to read as well and to comprehend. So I guess that would be that would be an interesting test already right there. Is reading my notes. Um, but if you look at, so you can actually, there's an option to the charts. So these are the absolute values, but you can also switch it into what they call the RCA value. And RCA value is comparing what is specifically important in this field. And this time is not really surprising because this huge bar over here is programming. So it's not very surprising that programming as a skill is differentiates your computer science from other fields. RCA is an interesting term. I looked it up, and turns out it's usually used to describe global economy, basically looking at countries and what they import, what they export. So it's usually used in that context, but in this particular context, it's basically saying, what is the distinguishing skill set of this particular field compared to the rest. So in this sense, programming does make sense. Yeah, sure. I can post the link itself in Discord, so you don't have to wait until I post the actual Joplin notes. There we go. So this is really interesting, and the data is not just coming from some random source. According to the article, the raw data is coming from the Bureau of Labor Statistics. So it's not just some random university doing a survey of like 20 people. No, this is actually pretty heavy duty stuff. All right, so that's that, and we're gonna move on to let's see, where am I here? Nope, sorry about that. Over here. All right, so we are looking into. Does anyone want me to go over the relations homework, or is that okay? Yes. Okay, that was quick. All right, I like those. I like decisive and quick responses. That's good. All right, so here we got. Let me just kind of take the test myself here. So we're gonna do a preview. Okay, so want to look at my approach. All right, so we'll take a look. Now, the one thing is, some people would think that, Batak, you have been teaching this class for how many years, and you probably have all of these answers, memorized. The answer is no. I actually do not have anything memorized. I do not rely on memory to get things done. I rely on my understanding of stuff, and I basically try to solve each problem on the fly, when the problem is presented, and that has always been my way of doing things. Sometimes it's not the most effective way, and most of the time it gets by. I mean, I can get things done. All right, so question number one, consider the not equal to relation over all integers. Which of the following relation properties apply? So when I think about this, I just I make I use certain numbers in my head. Okay, so instead of looking at all the integer and in a theoretical sense, I just think about, okay, let's just pick integers 1, 2, and 3. Okay, because if I can use concrete examples and I come to a certain theory, then I can work on it a little bit more. So so that's usually my approach. Is I try to kind of relate to concrete examples in my head first. Yeah, the lottery one, I don't think I can talk about it yet, okay, because there are some unfortunate situations where I had to make it, I have to give certain people extra time for that one. Um, oh, no, we got both assignments. I kind of emphasized that we have two assignments, from the previous week. Ah, ah, okay, so anyway, getting back to question number one. All right, so reflexive. Reflexive is asking, does a integer value relate to itself using the not equal to relation? So the answer is obviously not, right? Because if you look at 1 and 1, can I use not equal to relate the value of 1 back to itself? The answer is no. So it is not reflexive. Now we look at symmetric. So symmetric means if okay, let me go back a little bit. So symmetric means A relates to B if and only if B relates to A. All right. So that means if A does not equal to B, then B does not equal to A. Or I should say, A relates to B if and only if B relates to A. So in this case, it is symmetric. Because if you have two different integer values, they do not equal to each other, and it goes in both directions. Well, actually, I think there are other ways to check, what is currently assigned in the course. But I was pretty sure that I mentioned it, in class as well, verbally. All right, partially ordering. Now, partially ordering is a little hard to say. Actually, right now I can say it's not partially ordering because reflexive is out already. So we know it cannot be partially ordered, and we also know it cannot be totally ordered. So there's that. Now, is it transitive? The answer is no, it is not transitive. Because transitive means ARB and BRC implies ARC, right? So, but in this case, we cannot. It doesn't work because I can say A does not equal to 2, but 2 also does not equal to 1. Let me go back. 1 does not relate to 2, and 2 does not relate to 1. So does that imply that 1 does not relate to 1? The answer is no, okay? Because 1 does not equal to 2, 2 does not equal to 1, but 1 does not equal to 1 is not true. So we can throw transitive out. So now we are down to anti-symmetric. And anti-symmetric is definitely out too, because if you think about it, we have symmetry. Okay, so with symmetry, that really shows you a lot. Okay, with symmetry and without reflexive, anti-symmetric is pretty much out. Because with symmetry, it means, well, I shouldn't say, it is always the case, but since we have A does not equal to B, I should say 1 does not equal to 2 and 2 does not equal to 1. So that meets the left hand side requirement of the implication. But then the right hand side says 1 and 2 have to be the same, and the answer is no, 1 and 2 are not the same. So anti-symmetry is out. Oh, I should say 1 and 2 have to be the same, and they are not the same. So anti-symmetry is out. All right, so let's look at the text channel here. So we should just look at how to disprove the property. I would focus on that too. Yes, Jonathan is correct. If you can find concrete examples to disprove the property, then there's a very strong suggestion that that property is. I mean, if you can find one concrete case, to disprove the property, then that property would be false. However, just because we cannot easily find an example to disprove it, still doesn't mean that it is true. So you kind of have to think about the rationale behind not equal to, and see if you can, generally speaking, you can generalize and say that okay, I think this is generally true. All right, and then we have Aman saying if reflexive, anti-symmetric, or transitive properties are not present, we can just remove partially and totally ordered if any one of those is missing, not just when they're all missing. So because partially ordered requires reflexive, it requires transitive, it also requires anti-symmetric. So if any one of those three is missing, if at least one of those three is missing, we can throw out partially ordered. We can also throw out totally ordered, because totally ordered also depends on partially ordered. So there we go. What's asymmetric? Asymmetric is basically not symmetric, which is not the same as anti-symmetric. Okay, so there's a anti-symmetric is not asymmetric. So anti-symmetric has its very own definition when it comes to the universally quantified expressions. All right. Yeah, in a normal setting, then anti says it is not. However, in this specific case, anti-symmetric does not mean not symmetric. Did we even cover asymmetric? There's no asymmetric here that I can see. There's symmetric, there's anti-symmetric. I don't see asymmetric. Exactly. Yeah, we did talk about anti-symmetric. We also talked about symmetric, but not asymmetric. In lecture, did we talk about asymmetric? Well, let's check, right? I mean, that's the whole point. Alright, so I'm gonna check, because if I made a mistake, I will own up to it and go like, yeah, I made a mistake. Let's hope that is not the case.
We for sure didn't. It's just super easy to transcribe anti to asymmetric.
I see.
And
Okay.
yeah, so I looked up the difference between the words
I see.
last week. Yeah,
I
yeah,
see.
yeah.
But I want to make sure, because I definitely don't want me to have made a mistake and not realize and not admit to it. So if I did make a mistake, I need to make sure that I own up to it. Okay, but thank you. Yeah, so there's no asymmetric, there's only anti-symmetric. Now, this is one thing, this particular test on Wednesday is including relations. Okay, so um, I want to emphasize the importance of going for the actual definition. So, in other words, these quantified expressions, I think it is very important to understand how to read a quantified expression and also how to apply it, when you need to look at a particular relation defined over a particular set and understand how to use the definition itself to determine whether the relation is, of any one of these properties or not. I believe when we first talked about universally versus existential quantification, I gave you guys a pseudocode subroutine, one for each and one for there exist. And you might want to get back to it because because this class has a prerequisite of CISP400, I think, or 360, but it has a co-requisite of CISP430, which means all of you are assumed to understand your coding in general fairly well already at this point. So if you go back to that discussion and look at the examples or look at the explanation in the form of a pseudocode, C function, that might help you, fully understand um, what for all means and what there exist means. Now, when we see something like this, it's basically a double loop. We have an outer loop of for each e that is in X, and then we have an inner loop of for each f that is in X. So you can look at this type of thing as a double loop. Now, obviously, in the case of transitive, we have a triple loop. Okay, we have a loop within a loop within a loop. So the outermost loop, we go through all the elements of X and put those. Each one will bind to the variable e for each iteration, and then the middle loop is going to bind each value of the element into f, and then the innermost one is going to bind each element of X into g for each iteration. All right, so there's a bunch of tech stuff going on. All right, so I think the easy way to see it code-wise is for all means true until proven otherwise, and at least one or there exist means false until proven otherwise. Yes, I would agree with Jonathan's um, explanation. So if anyone feels that explanation is easier to understand and also easier to apply, go for it. But I can say that that is correct. Okay, it is a correct way to interpret the universal quantification and also the existential quantification. And Jonathan C is asking what day, and thank you, Matthew, for remembering what day. So this, okay, I really hate to say, I told you so, but this is why I told the class, you might want to jot down your, the date and time for each topic. Basically, you want to maintain your own catalog of the videos, because you don't have to take notes. I mean, there's not really a whole lot of notes taking, when you're taking my classes, because everything is recorded. So you can use that time to just kind of jot down, okay, today is November the 1st, and the current time is 4:46, and Tech is starting to talk about a particular topic. So that way, even if you don't need it later on, hey, no big deal, right? It will take you like 5 seconds to jot down that note. On the other hand, if you do need to go back and locate, okay, when did Tech talk about blah, you can just kind of search through your own notes and find out when. So yeah, you can also just kind of go through the Discord channels. Well, with the video, I don't think there's a systematic way to do it, but I think there's a way to download um, the closed captioning. So basically, instead of having to run through the entire thing, you can basically go through the closed caption. And Google is actually, YouTube, I should say, slash YouTube slash Google is actually getting pretty good with closed captioning. The automated closed captioning actually has a fairly high accuracy. So that might be another way to kind of search through the content without having to watch everything. So there you go. A timestamp guy. Come on, you guys, each person can do it, okay? It is the job of each person to do this. Okay, it's not. Let's not find a dedicated person to do this. All right. Yeah, the LaTeX guy is a little bit different. I'm the LaTeX guy. I mean, just right click, show math as, and then you go to tech commands, and there you go. And then once you know, some of these names, you can do your own search and find more. So there's that. All right. So getting back to these questions. Moving on to the next one. All right. So kind of the same deal, except this time it's equal to. So same thing. Yeah, we cannot evaluate partially ordered or totally ordered just yet. So the first thing is it symmetric? Okay. So in other words, um, A R B if and only if B R A, is that true? The answer is yes, it is true. Okay, because the only relations that exist would be between values of between the same value. So in that case, it is pretty much automatically symmetric. Is it anti-symmetric? The answer is yes. It is also anti-symmetric because anti-symmetric says for every way to find two values A and B, A R B and B R A implies A and B are the same. So in this case, the only relations are between values that are identical. So that means A R B and B R A would only happen when A and B are actually the same. So having A R B and B R A being true automatically implies that A and B are the same. So that is true as well. It's also reflexive. Every value does equal to itself. So we got these three items checked, which means it is partially ordered. But it is not totally ordered. Oh, it is transitive as well. So it is transitive, but it's not totally ordered. Alright, so we got some more text in the Discord channel. Fun fact, equal to is the only relation on a set that is reflexive, symmetric, and anti-symmetric. Okay, yep, that is true. And Aman asked, do we need transitive to be partially ordered? I am going to explain it, but it seems like we need a little bit more studying because all of these things were discussed before, and also the practice exam went over the same thing too. All right, so here's partially ordered, and I think the first question was what? Need transitive for partial? I don't know. What do you guys think? That's my answer right there. Okay, it is not an actual answer. It is a sarcastic way of doing Jeopardy. When Alex Trebek said, ask a question, I'll ask back, what do you think? All right. And my question was based on the fact that you didn't click transitive for partially ordering. Well, that's not sure. Not sure what that meant. All right. Partially ordered, and Wade has a screenshot. Yep, so that screenshot is coming from here as well. So that is true. Okay. It was just delay between when the question was asked and when text saw it. Yep. If people are watching YouTube, that's that's going to be a big delay. I'm not sure about screen share in Discord. I think the delay is not quite as bad. Okay. All right. No. Okay. Cool. No actual question then. All right. Excellent. All right. Let's move on. And let me double check and make sure I didn't miss one question. Oh, totally ordering needs the extra thing, which is comparable. A relation has to be comparable in order to be totally ordered, in addition to being partially ordered. And totally ordered is also defined here. So this is just a bunch of examples. So comparable is defined by this quantified statement. All right. Can I explain R is comparable over X for equal? It is not comparable. to prove totally ordered. So that's why it is not totally ordered, because equality is not comparable. Um, so I'm assuming the actual question is, why is it not totally ordered? Okay, well, it's easy to prove why something is not something, right? Because you just have to find a counter example. So let's just look at two values, 1 and 2. Okay, so can I relate 1 and 2 and say 1 equals to 2? No. Can I relate, these two using the opposite way, like 2 equals to 1? No. Well, I have just found one counter example where, neither of these things, of the or is true. I found, if E is 1, F is 2, this is false, and therefore the universally quantifier would say, the entire statement is false in that case. And then Jonathan said comparable ensures that each element is compared against is somehow related. Okay, so if you pick any two elements, let me go back. Okay, you have two variables. Each one is bound to a particular element in the set. So you have to basically say no matter which variable is bound to which element in the set, okay, these two have to be related in at least one way. So this is one way for the two to relate. This is the other way for the two to relate. If you cannot find either this or both, then they are not related in any particular way, in which case the relation is not comparable. Yep. So as I said earlier, this is the definitive way to look at whether something is comparable or not. And the way to look at this is to combine this with my explanation of with both quantifiers using using a C pseudocode function. So you basically plug in this into the pseudocode, and then you just run through a few integers, and then you say, okay, is the function going to return true, or is the function going to return false? That's the bottom line. I mean, beyond that, it's pretty hard for me to explain or to tell people how to understand something. A lot of times you just have to spend time, to kind of let it soak. But letting it soak also means you have to get it, at least in your mind in to begin with, and then you just spend time to kind of think about it. So given two elements, ERF or FRE must be true. I think that's what this is saying, right? I mean, this is an OR. So in order for the universal quantifier to be true, it means whatever expression, Boolean expression here, has to be true no matter how we choose the values of E and F. And the only restriction of E and F is each one has to be an element of X. So it kind of really, it all kind of goes back to the definition. So it's very, very important to understand the definitions of things. And at this point, these universal and also existential quantifiers they're utilized everywhere. I mean, we use it a lot, okay, in a lot of the explanations that are involved in this class. All right. So moving on to the next question, number 3. If R and S are both relations defined over X, and we also know R intersecting with S, which is another set, is reflexive, then what do we know for sure about R? Alright, so the first one is none of the other answer can be confirmed. That means we have to look through all of the other ones and make sure they cannot happen before we can choose the first one. So we're going to defer that. R is anti-symmetric. Okay, so the question is, can you find an example where R and S is reflexive, but R is not anti-symmetric? The answer is, yeah, that's pretty easy to do. So it is not anti-symmetric. R is transitive. Once again, you can make R, the intersection of R and S, reflexive and make R not transitive. So that's disproved. R is symmetric. Kind of the same thing. The only thing you can know for sure is R is reflexive. Because if R intersecting with S is reflexive, that means the components that we need in a relation in order for it to be reflexive is going to be in R as well as in S. So that means it automatically makes R itself reflexive. It also makes S also reflexive. In other words, if something is already reflexive, adding more elements to the relation cannot make it not reflexive. Whereas the other ones, it is possible for something to be, let's say, transitive, and then you add a few more elements, one or more elements, and then it suddenly becomes not transitive anymore. That is entirely possible. Same thing for symmetric, and then same thing for anti-symmetric. Reflexive is kind of the only one where if you start with enough elements to make it reflexive, it is not possible to make it not reflexive by adding more elements into the relation itself. All right. Um, how about go back to the practice exam from last week? Because we definitely went through quite a few examples from last week where the relation itself is reflexive. Well, Jonathan is already just gave an example. Very good. Now, if I were lazy and I want to just give people the minimum example, this is what I would do. Okay, x is this. Okay, you guys cannot see yet because I haven't really typed it in. Okay, there we go. That would be my example. Something that is reflexive. But it is, okay. I was only half joking, okay. Yes, it was a very very bad example from the perspective of it's the set itself is empty, and so is the relation. But it is actually reflexive because remember what Jonathan said, okay. Um, Jonathan W. Said earlier, if you cannot find a counterexample to disprove it, it is automatically. So, okay, that's how he looks at the universal quantifier, and that is true. So when you have an empty set as the set of elements itself, and then the relation is also empty, can you prove that this is not reflexive? The answer is no, because you cannot say it's lacking something, and as a result, it is reflexive. So I think Jonathan W. Just presented a very interesting and useful way to look at the universal quantifier is, can you show that it is not blah? Because if you can't, then it's automatically yes. So that's actually a pretty insightful way of looking at it. Question number 4. Consider the less than relation over integers. Which of the relation properties apply? Well, we kind of know it's transitive, right? Because if A is less than B and B is less than C, that kind of implies A is less than C. Okay, that's something that we intuitively know, but if you can also go through some examples to convince yourself of that. It is not reflexive. A value cannot be less than itself. Is it symmetric? Nope, it is not symmetric because if A is less than B, it is not B is not less than A. So it is not symmetric. And as a result, we know for sure it is not totally ordered nor partially ordered because it is lacking reflexive, and even though it's transitive, it's lacking reflexive already at this point. So that means we already know for sure it cannot be totally ordered, it cannot be partially ordered. And then the last one is anti-symmetric. The answer is yes, it is anti-symmetric. Let me think about it. Yep, it is anti-symmetric. Because anti-symmetric says if A are B and B are A, then A equals to B. But in this case, you cannot find me an A and a B value, okay, both being integers, where A is less than B and B is less than A. That simply does not exist, right? So as a result, the left-hand side of the implication is always false. When the left-hand side of an implication is false, then the implication itself is true. So there you go. Exactly. There's never, you cannot find me an example where the first part of the left hand side of the implication is true, and as a result, we don't have to worry about it. The implication has to be true all the time. Yep, implication. So now regarding implication, um, different people work differently. Okay, their mind work differently because I guess part of it is language exposure, and the other part has to do with some people just naturally go for the technical definition of terms, and other people go for the more um, intuitive understanding of the words. So depending on which type of person you are, you can understand implication a little bit differently. I would go for the definition. I would simply go to the truth table as the definition and just look at the truth table, right? The truth table says, okay, for all the two cases where the left hand side is false, the entire implication is already true. So that means it doesn't matter what the right hand side is. If the left hand side is false already, the whole implication is going to be true. So I would look at it that way. Some other people look at it as not A or B. When you have A implies B, some people like to translate that into not A or B. That's perfectly okay as well because it will give you exactly the same definition. It will give you the same truth table with the alternative expression. So you just have to find a way that works for you. Okay, I think the worst is going to be using the actual word implies and use the English definition as a way to understand how implication is used in the context of this class. That might be the worst way to look at implication because that can certainly lead to confusion. Yep. I like truth table too because it's only 4 entries and it really spells out every single way you can arrange values on the two sides of implication. It doesn't leave anything to imagination. I'll put it that way. And then we got number 5. We have greater than or equal to. So with greater than or equal to, okay, let me check. Truth table for big C and F on the other hand. Well, it depends on the number of variables, right? Because if I give you just 2 variables, yeah, I think it's still doable. 3, eh, still doable because you only got 8 rows to deal with. And then 4 variables will give you 16 rows. 5 variables will give you 32 rows. And then at that point, it maybe the trade-off may favor solving the CNF to instead of using the truth table approach. Alright, so question number 5. Consider the greater than or equal to relation over integers. Which of the following relation properties apply? So in this case, anti-symmetric does apply, okay? Because this time we can potentially have ARB and BRA both being true. But that happens only when A and B are the same, because the same value is greater than or equal to itself. So that's why it is anti-symmetric. It is reflexive because each number or each value is greater than or equal to itself. It is also transitive because if A is greater than or equal to B and B is greater than or equal to C, then we can conclude that A is greater than or equal to C. And because all 3 are true here, we know it is partially ordered. Now, symmetric is kind of hanging out there because symmetric is not needed in order for something to be partially ordered. In this case, it is not symmetric because just use examples, right? So you can say, okay, look at 3 and 4. 3 is not greater than or equal to 4, but 4 is greater than or equal to 3. So that means it is not symmetric. And is it totally ordered? The answer is yes, it is totally ordered because if you just give me 2 values of integer, they don't even need to be different. I can tell you which one is greater than or equal to which one. So that's why it is totally ordered. Exactly. So Aman is correct. 4, 3 is in the set, but 3, 4 is not in the set. So that means the if and only if is going to be false. And as a result, if you can find one instance for the Boolean expression inside a universal quantifier to be false, then the universal quantifier itself is also going to be false, or the quantified expression is going to be false. All right, number 6. Number 6 says if R is a relation defined over X is known to be reflexive, so R is known to be reflexive, which one of the following do we know for sure, regardless of the actual definitions of R and X? So we just know one thing, which is R is a relation defined over X. It is reflexive. All right, so let's take a look at this. The cardinality of R is greater than the cardinality of X. That looks good, okay, but we are gonna check out the other ones, okay? The second one does not equal to, the cardinalities do not equal to. Well, that's not always true because I can always just add one more thing to R. It would still be reflexive, but it won't have the same cardinality anymore. Yeah, Jonathan's right. The next one is equal to. Now that's not always the case, right? Because I just said that one thing. Oh, I take it back. With the previous example, if R is just reflexive and nothing else, each element relates to itself, then the cardinality would have equal to, and as a result, not equal to would be false. Now with this one, with the third one, the cardinality of R does equal to the cardinality of X. Yes, that can be arranged. However, it is not always the case. Okay, because I can just throw in one extra thing, and then suddenly you have a relation that has a cardinality that is greater than the cardinality of X. And Jonathan is correct. So that is a counterexample of why the third one cannot be the answer. And the fourth one just doesn't make sense, okay? That one just doesn't make sense because in order for every element to relate to itself, that means the number of elements in R has to be at least as much as number of elements in X. So having the cardinality of R is less than X is always false, okay? If I was asking for something that is always false, it'll be the last one, it'll be the fourth one. Since we have found one that we know is true already, then none of the other answers can be confirmed. It's going to be false. It doesn't apply. All right, moving on to the last one. If R is a relation defined over X and R is known to be symmetric, which of the following do we know for sure? Can we know for sure? Do we know for sure? Regardless of how R and X are defined. This one is tricky. This one is actually this. None of the other choices can be confirmed. So let's check out why that is the case. Okay, because no matter how X is defined, if R is empty, it is symmetric. So that automatically throws out the first one as well as the second one. Now, what about the third one? Well, the third one can be thrown out pretty easily as well, because if R is empty and X is empty, then the cardinality of R cannot be less than X, and yet an empty relation defined over any set is always symmetric. So we throw out the third one because of that. And then we have the next one, which is to some people it might make sense intuitively, but it does not. It doesn't work because this one relies on the fact that because if it goes in one way, it has to go in the other way too. Well, when those two elements are different, that would be the case. Okay. However, remember, an element can relate to itself, and that would still be considered symmetric. So that's why there's no guarantee that the number of elements of R has to be exactly twice of the number of elements of X. R is odd? Nope. It can certainly be even because an empty relation has a cardinality of 0, and 0 is even. And then the next one says they have to be the same. Nope, they do not have to be the same. Because X can have any number of elements in it, and if empty set R is already symmetric, then 0 equals to non-zero, because X is non-zero, is going to be false. The next one here is R is even. So once again, it doesn't have to be even, because let me take a look at Jonathan's example right there. Okay, so Jonathan's example of x being 0, 1, r being 0, 0, 1, 1, and 1, 0 has r being not even. The cardinality of r is not even in that case. And it is not symmetric. Oh, okay, never mind. It is not symmetric. Um, so in order for to reuse that example, okay, I'm gonna type it in the text channel, or I can do it in Joplin. Joplin is probably easier. There we go. All right, so in here, I'm gonna give you an example. So we first define x. X has one thing, and then we want, what do we want again? We want r to be even. Okay, so is that right? Okay, so we want r to be even, and we want r not to be even. Sorry, in this case we want r not to be even. That's pretty easy. Okay, 1, 1. So the cardinality of r is not even now. There we go. And Adam says you could even remove one of the reflexive tuples, so it's not 2 times x either. I'm not sure about that. Jonathan is correct. That's another example of r being having a cardinality that is odd. All right. So, are there any questions about relations? Any questions about how to study? Because I think it really boils down to how we study. I think if I were to study for this class, I would actually go straight to the definitions and make sure that I fully understand the definitions. Just keep doing problems until definitions become second nature. That might work for certain people. It does not happen with my brain, unfortunately. I'll give you guys an example. I know I'm digressing a little bit here, but it might make sense to some people. When I was in high school, physics was one of the subjects that I took for the high school exit examination. And a lot of my classmates, in addition to doing all the problems in the textbook, they also ordered additional, books, and they finished every single exercise that they could find, that they could get their hands on. I did not even finish, the ones in the textbook. So how did I study? I really just kind of look at the concept and stare at it until I have an understanding of the concept behind it. It took me a long time to understand acceleration because the concept of rate of change was new to me at the time. But once I figured out what rate of change really was, then it became easy. I never memorized, other than the most basic equations or the most basic definitions. I never really memorized any equations in physics. And yet, when we took the exam, I scored, just as well as all of my classmates. So different people work differently. Our brains can be wired, in a certain way that, for some people, it's all based on hands-on stuff. They have to do, they can do it many times, and then they learn it that way. For me, it is not. Busy work actually makes it worse. For me. So you guys kind of have to know how your brain works. So you can look at this class, okay? This is the silver lining. You can look at this class as an opportunity to find out, how your brain works, how you learn in a class. All right. Oh, okay. Yeah. Yep. Well, in Hong Kong, exit examinations or high school exit examinations was actually pretty grueling because most people take, maybe I took 8 subjects and each one has 3 years worth of material in it. That was actually I got it easy. Okay, some crazy kids actually took 9 subjects or even 10 subjects, and they tried to get A's in every single one. Now in Hong Kong, the grading system is different compared to the United States. So in the United States, you guys have A, B, C, D, F, right? We have A, B, C, D, F here. In Hong Kong, it goes all the way from A to H. Okay, so we have A, B, C, D, E. All those are passing grades, and then we have 3 failing grades. F, G, and H are failing grades. So some people can just barely fail. You're getting an F, and then some people can fail miserably by getting an H in their exit examination. And I cannot remember the percentage, in terms of the number of people who can get A's in as a percentage, because they only grade by curve when they assign letter grades. They never really do an absolute threshold. Yeah, maybe. It's a matter of perspective. I did not fail a single subject, but I did get everything from A to E in my exit examination. Alright, so did I get a good score this time? Did I show that I know my stuff? So it would seem. Alright, there we go. Alright. Alright, so now that we have this taken care of, we can now get back to where we left off last time. Will these assignments count toward final grade? The answer is yes. All the assignments will add up to 20% of your final grade. Now they should. So maybe I just need to move the assignments to a different category, but they do count for 20%. All of them added together is 20% of your final grade. Alright, so we still got 2 people typing, so I'm gonna wait until those are in. Not seeing any new text yet. Alright. Alright, so there we go. Nah, I'm not gonna take row today, so we'll be fine. Alright, so part of the idea of taking row is to see if I can help people build an habit of coming to class, at this time of the day. And for people who cannot, build up that particular habit, at this point, it's gonna be very difficult. All right, so Wade said, I've gone down a linguistic rabbit hole around the pronunciation of the words. Compare, comparable, comparative, and comparable. There isn't a lot of official documentation aside from a few main dictionaries listed both pronunciation, although the second is listed as distinctive US in Cambridge Advanced Learners. Okay, that's interesting. Comparable. I always thought it was comparable. All right. Comparable meaning able to be bought. Okay. Oh, okay. That's the one without the extra A. Oh, okay. Interesting. Cannot be bought. Oh, can be bought. Never mind. Can be bought. Calmed it. Interesting. All right. All right. So we are now moving back to the concept that we first introduced last week. Ah. Okay. So 3.3 talks about the limit of a sequence. I believe we talked about this. The idea is if the limit itself, if the sequence is has a limit of k, that means if you just give me a very small epsilon that is greater than 0, and you ask, hey Tech, can you find me an index, of this particular sequence, so that starting with that particular index, everything after that is going to be at least, this much away, at the most. Sorry, let me get back. At the most epsilon away from k, and the answer is if I can do that, that proves that k is the limit of the sequence here. So that was what we talked about last time, and the universally quantified expression looks kind of yuckish here, because in this case, I can explain that. I mean, it's basically saying, for every y in R, there exists an m in n such that for all j that is greater than m, which means everything including m and all the elements to the right hand side in that sequence, xj is greater than or equal to y. Oh, I take it back. This one is for infinity. Never mind. We haven't talked about this yet. Okay, so we have talked about this particular quantified statement. Sorry, I got myself confused. This was the one that we talked about last time. For all epsilon that is greater than 0, which is a real number, there exists m as an index as a natural number, such that for all the indexes, for all the elements in the sequence where the index is at least m, the absolute value of k minus x of j, so k is this specific value over here, x of j is the value of a particular element in the sequence, that is guaranteed to be less than epsilon. So that is the very definition of this thing here. So this thing here just has a really, really long equivalent expression here. So are we doing okay so far in terms of just understanding when the limit of a sequence is a specific value? Okay, processing. Very good. It's better when you use a graph. Okay, so if you think about the graph, the value of the sequence can go above and also below k. It's just that as you proceed with an increasing index, they fluctuate less and less, and they basically it at a certain point it would seem like it is already k, except it can still be varying just a little bit, but the amplitude of the varying is going to decrease as the index I continue to get larger and larger. All right. Um, hmm. I think next time I will see if I can give you an actual example so I can define, how we compute the values in the sequence. Then you can see, how you can say, you can arbitrarily, pick an epsilon and say, hey, Tech, this is the epsilon I have chosen. Okay, it's 0.001. And you can then ask me and say, Tech, can you find an index m such that x of m is within epsilon away from k, but on top of that, okay, everything to the right hand side, so everything in the sequence that has the index of m, m plus 1, m plus 2, m plus 3, and so on, they all are within epsilon away from k. That would be the question. Okay, if I can answer yes, okay, I can prove that is the case, then I have just proven that the sequence x, has a limit of k. Or you can say, x, the sequence x, is going to approach k. All right. So is that okay? Does everybody kind of get a hang of this? All right. Okay, so we're going to move on to the next paragraph. So if I define x of I, as negative 1 to the power of I, then in this case, the sequence has no limits because it keeps fluctuating between 1 and negative 1. So that means, someone can quite easily pick an epsilon, and then I would not be able to find an index m such that, xm, xm plus 1, xm plus 2, and so on would be only within plus or minus epsilon away from whatever k you want to use. Because in this case, the amplitude of the oscillation does not change. It is always going between 1 and negative 1. So if anyone were to pick an epsilon that is less than 1, then I would not be able to make this entire statement true. So that's why, if you look at a sequence where each element of the sequence x of I is defined to be negative 1, the whole thing to the power of I, then that particular sequence has no limit. Yeah, it kind of needs a way where it attenuates. The fluctuation attenuates. It gets smaller and smaller, or I should say, it gets closer and closer to whatever this value k is. You can also say the limit of a sequence can be infinity itself. So in this case, it's easy to pick one because if I just define x of I as I itself, then the limit of the sequence is going to be infinity. So in this case, the definition of the limit of a sequence is slightly different because of the difference of infinity and any finite number is infinity. In other words, you cannot say, oh, this number is infinity, and if I subtract a finite number from infinity, the result is undefined. Okay, so that's why we have to sort of change the definition a little bit. So when we claim that a sequence has a limit of infinity, this is what it means. It means for all y that is a real number, you can find me an index m such that if for every element in the sequence where the index is at least m, that particular element in the sequence is going to be greater than y. So give me a large value, okay? In plain English, give me a really big value and say, hey, Tech, I challenge you to find a index m so that, x of m plus 1, x of m plus 2, and so on, they're all going to be larger than the huge value that I just gave you. If I can prove that is the case, okay, no matter how large of a value you have chosen, I can always find not only an x of m that is larger than the value that you have chosen, but I can also guarantee that everything that is to the right hand side of that particular value in the sequence, they're all going to be greater than the huge value that you have chosen. Then I have just proven that the limit of this particular sequence is infinity. Is that okay? Is that understood? Okay, very good. All right, so you might find this kind of math to have a flavor of calculus or certain concepts in calculus. The next one is limit superior. So limit superior is we define limit superior of a series of numbers. Basically when I use the word series, it really is the same thing as a sequence of a series of numbers x of n as follows. So the limit superior of x of n when n approaches infinity is defined to be this. So the first thing we need to do is to say, okay, what is that? Now I hope you guys still remember what is supremum, because sup here is supremum, and then inf here is infimum. Now we also talked about, because we are dealing with actual real numbers here, so that means supremum is basically the maximum, and then infimum is basically the minimum. So I am taking the maximum of a particular set, and that set consists of x of k where k is greater than or equal to n. And after that, I take I take a look at all of these maximums, and then for n greater than or equal to 0, so n can be 0 itself, n can be 1, can be 2, and so on. So now I take a look at all of those supremums, and I take the infimum of the supremums. So in easier terms, we are taking a bunch of maximums, and then we take the minimum of the maximums. Is that okay? Yes? Okay. So that is the definition of limit superior. So limit superior is basically the minimum upper bound of a sequence of numbers. Let me say that one more time, okay, because this is going to be helpful. It is the minimum upper bound of a bunch of values. Because when we talk about upper bound, okay, it can be way over, right? So let me just give an example here. Okay, so I want to give this. I want to find an upper bound for the age of this class. Okay, myself included. So I can say, I would say 500. And is that an upper bound? Probably. I mean, unless somebody in this class is 501 years old, 500 is a legitimate upper bound. So is 499, so is 498, and so on. So of all the upper bounds, okay, I want to find the minimum of the upper bounds. So the idea is, I want a tight bound. I want a tight upper bound of the values that we're dealing with. So let's just say that I'm actually the oldest person of this entire class, okay? Then, let's just say that I'm 55 years old. Then 55 is going to be the limit superior of this particular series of numbers. Are we doing okay so far with this? All right. So limit superior is loosely translated into the minimum upper bound, but it applies to the tail of an infinite series of numbers. Okay, very good. So that means, early on in the series, that might be, what we finally decide as the minimum upper bound, may not apply to some of the numbers early on, but it applies to the tail end of the series of numbers. All right, so with this one, let me take a look at the time. Yeah, we got time. All right, so we can actually use an example to illustrate this one. Now, obviously, I cannot give you something that has an infinite I cannot give you an infinite series, okay, but I can give you something that is finite, so the idea still applies. Or I can say, after this point, everything has the same value of something. So let me go back to Joplin, and I'll give you an example. So this is example of limit superior. So lim sup is the term here. So we'll go ahead and define the sequence. Okay, so x is I'm going to use the array notation because a sequence is essentially an array, and we're going to use this notation here to indicate what values are inside this particular sequence. So I'm going to start with, say, 500, and then we drop all the way down to 0, and then we have 499, and then we have 1, and then we have 300, and then back to 5, and then we have 200, and then a 10, and then we have 100, 100, 100, and so on. Okay, so after a certain point, they all become the same. So now the question is, what is limit superior of x while n approaches infinity? So that is the question. So we're going to expand it. So now we go back to the definition. So when we expand it, we first have to find the minimums where the start index, can go from 0 and then 1 and then 2 and so on. So now we are asking, so the outer portion is still trying to find the supremum, but inside each one is basically saying, if I start from the first one, what is, let's see, let me double check here. What is the minimum? Okay, so what is the minimum if I were to start from element 0 in this case? So if I were to start from here, the minimum is going to be, oh, that's pretty clear. It is this 0 over here. Minimum, not maximum. So I think I got the terms reversed. This is the, yeah, no, it's not your bad. I explained it incorrectly earlier. So it is the minimum. Okay, so we're trying to find the minimum starting from the very beginning of the entire thing. So that would be 0 itself. So if I were to be more clear about what this is the infimum of the set starting from 0. So this is the infimum starting from, of 500, 0, 499, 1, and so on. And then the next one is going to move the index. Okay, so for the next one, we are trying to find the infimum starting from the 0. Okay, so from 0 and then 499, and then we got the 1, and so on. And then the next one is also an infimum, and this time we are starting with 499 and then the 1 and so on. And then the next, you guys get the idea, I hope, right? So all I'm doing here is to control the starting point of where in the sequence am I trying to find the minimum, and each one is basically shifting to the other side by 1. I think the editor is not cooperating. One more, there we go. Okay, still doesn't work entirely correctly. And we have 1 and 300, 5, and so on. It's not bubble sort. Okay, this is basically just me expanding what the meaning of limit superior is. All right, so then we have a whole bunch of items like this, and then this becomes the set where we want to try to find the maximum. This is minimum, this is maximum. So this boils down to, okay, if we actually evaluate this, okay, it boils down to the first one is going to be 0, because 0 is the smallest. If we are to start from the very beginning and look at this entire series of numbers, 0 is the smallest. So we are looking at 0 here. Then we have 0 again, because the next one starts with the second item from the series, which is 0 itself. And then the next one is going to be 1 and 1. Okay, so we have 1, 1. And then we got 5, 5. And then we got 10. And then after that, okay, we start to have exactly the same value. So 100 is going to be both the minimum and also the maximum. So now we have 100 here. So does everybody understand how I got this particular 0, which is the minimum of this bunch, and then this 0 is the minimum of this bunch, and so on. That is true. Okay, so Jonathan is correct. A set can only have unique elements. So, so far I have not listed anything that is duplicate yet. Oh, right. Okay, so I got it. So we have duplicate items here, and then we have this one here. But I want to kind of, I'm trying to explain why I had the double 1 and the double zeros. Because even though, yes, a set can only have unique elements, but we are actually making a union of two identical values because we are making a set out of these items and they can potentially be duplicate. So in this form, there's no way we can actually encounter a situation where we can see, hey, these two have the same value, and they cannot be in a set. But once we expand it out like this, then we can evaluate this and we say, hey, this thing actually has the same value as this thing over here, and as a result, in the set notation, we cannot have both of them being identified, as different things inside the set because the same value can only appear up to once in a set. So is that okay? But the idea is still the same. I'm just trying to gradually work on this manually. So now we look at the minimum of all of this stuff here, and the answer is 0. Let's see. No, this is finding the maximum. Let me just correct myself. This is finding the maximum. So in this case, 100 is the answer of limit superior because we are eventually trying to find the maximum of the minimums, and each one of the minimum has a different starting point in the sequence. All right. Okay. Yeah, so next time I'm going to give you guys another concrete example to illustrate it, because next time it's going to be at least next Monday, if not next Wednesday, because I probably will use Monday to explain the key to exam 2. So it's probably either Monday or Wednesday. So I'm going to use a concrete example at that point, and so this way it's not just another example, but it's also a reminder of where we are in the notes. So if this is limit superior, you can probably guess what is limit inferior. It's basically just flipping everything. So I think I misspoke a little bit earlier. This is the minimum upper bound of the maximum lower bound of the tails of an infinite series of numbers. And then we define an upper bound. Okay, now this is where we get into the big O notation. And we have a few minutes, so this is good. So limit inferior is how we define upper bound, which is what big O is about. Okay, so let's take a look at this definition here and find out what the big O notation actually means. Limit inferior example. You're right. Okay, because limit superior is here. So I overscrolled. Yes. So Adam is correct. The example that I gave is limit inferior, which is the maximum, is the tight bound. Let me see. It is the maximum of the minimums, as opposed to limit superior, which is the minimum of the maximums. Yep, Adam is correct. So I have been using this, as an example, and that's why the example that I just gave, which is over here, this is actually limit inferior. I was incorrect to call it limit superior because this is actually limit inferior because it is trying to find the maximum of the minimums. Let me just double check. Yep. Okay, now it makes sense, right? Because this notation here is matching this notation over here. We're trying to find the maximum of minimums as opposed to the other way around. I apologize because I overscrolled. I thought I was trying to talk about limit superior, but I was actually looking at the definition of limit inferior because I didn't look at the header of the section. All right, so Wade is still typing. But by the end of today, okay, we got a few minutes. I do want to go over this, okay, because this is the concept of the big O notation. So in this case, we have two functions. F of n is usually a really nasty looking, complex, kind of, function. And then g of n is usually something simple, like, g of n is 1, or g of n is n, g of n is n squared, g of n is log n, or g of n is n log n, and so on. So g of n is usually something that is a lot simpler to describe, and then f of n is the actual very accurate estimate of how long an algorithm will take to complete. So we can call f of n an element of big O of g of n if and only if the following is true. So in order for the following to be true, this is basically looking at the upper bound of the absolute value of f of n divided by g of n. If this is less than infinity, then we're good. Then we can call f of n to have g of n as the upper bound. So big O notation is all about the upper bound. All right, so are we okay with this so far? You can kind of imagine, okay, so think about cases where f of n is just n and then g of n is n squared. Okay, so just kind of substitute actual things into f of n, which is just n. It's a linear function, and then g of n is n squared, so it grows faster. So in that case, when n is approaching infinity, n divided by n squared is 1 divided by n, and when n is approaching infinity, the 1 divided by n becomes 0, basically. But the question is 0 less than infinity? You guys go like, oh yeah, it's infinite. It's definitely less than infinity. So in that case, we can say n squared. The big O notation is trying to establish an upper bound. So even if you have an algorithm that actually has a time, actually will take a time that is linear to the size of the problem, you can always say that it is big O of n squared. Now this is really odd because this is not how most people understand the big O notation. So the misunderstanding comes from the fact that most people do not understand that big O is simply trying to establish an upper bound. And that upper bound can be very, very unreasonable. Alright, so Wade is still typing. I'm going to actually stop talking because I have just expressed what I wanted to express. Okay, the one thing I wanted to express before the end of the class was the big O notation is not what most people think it is. Okay, big O is just an upper bound. If g of n is an upper bound of f of n, then we can say f of n is an element of big O of g of n. It doesn't say anything about how close that upper bound is. And now we got two people typing. So the maximum minimum, the largest value minimum present within the set of all subsets of a given x, where the set of subset is defined as that. Except the sequence also has no end. That's the problem. Wait, the sequence has no end, but you got the concept. Okay, basically, the subset or the sequence, the subsequence, I should say, the subsequence in which we're trying to find. I think you're trying to talk about the limit superior. So so let me go back to limit superior. So you're trying to find a bunch of maximums first, okay? And the maximums you're trying to find is from subsequence of the original sequence. So the first one would start with k being greater than or equal to 0. So k is going to be x0 and then x1, x2, x3, and so on. And then the next one is going to have, the smallest k is going to be a 1. So that means you're dealing with x1, x2, and x3, and so on. So each one, this one starts all the way from the beginning. This one starts from the second element in the sequence. This one starts with the third element of the sequence. This one starts with the fourth one, fifth one, and so on. So now you basically end up with a infinite number, each one being a maximum of a subpart of the sequence, starting with a particular index and all the way to the end. So you take all of these maximums and then you ask what is the minimum of all of these maximums. And assuming you have something that approaches a particular value, then you basically can say, oh, okay, I can see asymptotically speaking, as n becomes very very large, I can now claim, okay, the limit superior is the quote unquote upper bound of the sequence. Yeah, it feels like calculus, exactly. Yep. Except in calculus, we're dealing with much more well-defined functions. So every element in the sequence is well-defined. In this case, we're just talking about some arbitrary value in a sequence. Yeah, I think that would be a good. This would be a good end of today's lecture. Is basically just to look at this. All right, we got a few people dropping off, but I'm still online because now is my office hour. And these functions are a little less defined because of the discrete nature of the math. Well, g of n typically is something that is well defined. It's usually one. If you have a constant time, then we want to g of one or g of n being one is how we express the a constant time thing. And constant time is basically the it can only be the upper bound of something that actually is constant time. But g of n can also be n squared, n log n, just log n, and so on. So g of n is not the problem here. G of n is usually fairly well defined and easy to look at. F of n is the ugly one because f of n is the one that we don't want to look at, and all we want to do is to go, okay, I can prove this. Okay, if you can prove this, then we don't want to actually look at f of n itself, because f of n is usually much more complex and much more ugly because it is the actual time that an algorithm is going to take to finish on a particular architecture. So now you have to take into consideration of all the little bitty things that really do not matter in the long run. So f of n, probably have a component of g of n in it, but what you need to show is the other components of f of n cannot grow as fast as g of n. Then you can now that's how you can claim g of n is an upper bound of f of n. So is that helping, Wade? All right, cool. Yeah, this stuff is not going to be in the second exam, so we can always come back and look at this a little bit more. But the main point of today's lecture is what most people think is big O is not actually what big O is. All right. So as you guys study, you can still kind of contact me to have concepts clarified. And okay, we still have Wade and Jonathan participating. That's great. Most of the time before things start to scroll off my screen, once they scroll off the screen, all bets are off. But I have learned not to use Outlook Web Access, as my email client. That was just awful. Not looking super close of f of n helps avoid the PNP problem. So PNP, well, I'm still online, but you guys can all kind of sign off if you want to. So the P versus NP problem, the NP problem. Okay, so let's start with what NP is representing. It is not within the scope of this class, but some of you, all of you, actually will eventually get to take a class, that actually talks about what is P and NP. So NP is standing for non-deterministic polynomial time. Polynomial time. And time is going to be outside, right there. All right, so that's what NP is representing. It just says non-deterministic polynomial time, which loosely translates to, okay, if you want to think of technology and use that to understand what this means, it means you have a processor that has an infinite number of cores, and it will take you basically no overhead to start a core on a particular thread to do a certain thing. So even with an architecture like that, if you can say, well, with an architecture like this, I think I can finish this within polynomial time, then you have an NP, time complexity. So it relies on the fact that you can have, infinite parallel processing, and then for each thread of the processing, it will still take polynomial time to finish the computation. So typically, we are looking at problems like the traveling salesman problem. So with a traveling salesman problem, it is called NP complete. So when we have the word complete after that, it means it is basically one of the many problems within the same classification of difficult problems to solve. Every single problem within the NP complete set, they can each transform to another problem within deterministic polynomial time. So you can take one problem within the NP complete set and say, okay, I start with this problem, but how do I transform this problem into another problem within the NP complete set? That transformation has to take only deterministic polynomial time. Now they don't really say about what is the order of the polynomial time. So it can be n, because n is basically a very degenerated polynomial of n. It can be n squared, it can be n cubed, but it has to be n raised to a fixed exponent. So as long as you can guarantee a problem can transform into another problem within deterministic polynomial time, then it belongs within this large group of problems that we call NP complete. And the poster child of all of these problems within the NP complete set is the traveling salesman problem. Now, the traveling salesman problem is kind of interesting because some people think of this and go like, well, don't we have a solution of these kind of problems already and it's easy? Well, most people are thinking about finding a shortest path. Okay, so finding a shortest path is a problem that has a very known, easy solution, and it is not very difficult at all. So you're basically saying, okay, I want to go from Sacramento to New York City. Okay, based on the current traffic and weather condition, what is my best route if I want to arrive as early as possible? That is not a very hard problem. Okay, because now you have all the flexibility in between and go like, I can go all the way south, avoid the snow and all the nasty weather, and then go back up again. The traveling salesman problem has a limitation, has a restriction. You have specific things that you have to traverse, but once and only once. So now you're talking about a tour. Let's say you're a band and you're making a tour of 5 cities. Okay, and now you have to find a plan where you have to traverse, you have to visit each city once and only once and get back to the first one where you start. And we are trying to find the best way to tour the 5 cities. That turns out to become a very difficult problem. It's an optimization problem, and it is NP complete because to verify the answer, okay, what you think is the best solution, is only going to take polynomial time because you're just trying to figure out. So imagine you have all of these different ways of traversing the 5 cities, okay, and that turned out to be 5 factorial. So there are 5 factorial routes to tour the 5 cities. So 5 factorial is what, 120, I think. So you have 120 permutations of going through the cities. It only takes polynomial time to find out how long each route is going to take. And then once you have the solutions, you can basically use polynomial time also to find out what is which route is the best, because you just have to confirm one is the best. So that's the general idea of why of the nature of an NP complete problem, because now you're relying on the fact that you can have one thread, one processor core dedicated to the computation of the distance of each permutation. And based on that assumption, then the problem would only need polynomial time. So that's kind of a topic that you will see again in as an upper division class at a four-year university. But this is just a kind of an early exposure of that. And all you have to do is to think about FedEx or UPS. They all have to deal with the traveling salesman problem. Oh, sure, absolutely. It's related to what we are going to talk about in this class, but we are not going to get into these specifics in the class. Yeah, those problems are also called intractable. Let me type the word here. Intractable. That could be a misspelled words. Well, they do have practical values too, because any type of most optimization algorithms fall into this category. So I can give you one optimization problem that is very practical, and we would like to solve those problems. It has to do with register allocation when you're writing a compiler. So most modern architectures have, they use general purpose registers, which means, you can use any register for addition, subtraction, multiplication, division, and so on. But you have a bunch of registers to choose from. Let's say, 32 registers, which is not even extreme, in the context of modern architecture. So now you have 32 registers within the processor, and you're analyzing a program, let's say a C program, and you're looking at how the values are being utilized, and what is being computed, what is being recomputed. So you're trying to reuse the registers as much as possible so that you don't have to recompute something. And that problem turned out to be NP complete. Okay, if you want to find the best way to utilize the registers so that you can minimize the amount of recomputation, it is an NP complete problem. So it does bite us, fairly often, because every time you look into a optimization problem, there's a very good chance that it is an NP complete problem. The best part about NP complete is no one to date, okay, that's including all the smart people in history, has solved that problem. So when you can prove, okay, if you work for a certain employer and the employer wants you to derive an algorithm to solve a problem, and you can prove that it is an NP complete type of problem, then no one can blame you for not being able to find a reasonable time solution for that problem. So it's a pretty good escape hatch when you're assigned a very difficult problem to solve. Yep. All right, cool. So I'm pretty much done with the lecture. So, if you guys don't have any questions, I'm going to sign off from the voice and video channels. Well, fortunately, TTP only has 4 registers, and we are going to use up one for one very specific purpose, the stack pointer. So we're only left with 3 registers, and in that context, there's really not a whole lot of optimization, because remember, NP complete usually is n factorial, and in this case n is only 3. So n factorial is, worst comes to worst is like 6. Okay, so it's not too bad in that case. Every problem is NP complete. All right, cool. So I'm gonna get out of the voice channel in Discord and also stop the streaming to YouTube, but I'll still be online if you guys want to continue any type of conversation. So I'll be online for another hour or so. All right, you're welcome. All right, so study for the exam. If you have any questions about the concepts, I can try my best to help clarify. But there are certain things I cannot help, which is how people learn concepts, because different people learn differently. So, all right, cool. I'm gonna get out of the voice now.